Have you ever wished you had a wise mentor to give you advice on your career? After all, wouldn't we all benefit and learn from the experiences of the ones who failed and succeeded before us? With this in mind, we've created a new series called OnTrack Insight. We will be sharing conversations with leading experts from the electronics industry to discover the wisdom, knowledge, and personal stories that have shaped their lives and careers. Our first guest is one of the world's leading experts in PCB design and signal integrity. His insatiable curiosity led him into a wide variety of sectors, including telecommunications, automotive systems, and military aviation electronics. He has read over 100 books on electrical theory and engineering. He has held numerous seminars at the largest industry events, including AltiumLive, at which we recorded the interview that you're about to watch. He will share with us his understanding of how electronics behave, how we can encourage the next generation to stay curious, and what he thinks is the key to a successful engineering career. Now, meet your mentor, RickHartley. Well, Rick, thank you very much for your time.
My pleasure to be here.
And I hope you're enjoying the show. How often have you come to AltiumLive?
This is my second year out of the 3 years of the show. This is the second time I've been here.
And you came in 2017, 18, 19?
I came in 18 and this year I was not able to be here in 17, unfortunately.
What is your impression of this latest installation?
It's a terrific conference. I think what you guys are doing, there are several, as you guys know, terrific conferences around the country. This one's a little different in that it focuses not only on technical knowledge, but on use of the tool. So it's really a combo sort of thing, which I think is great for Altium users in particular, but it's good for anybody who wants to pick up technical content, and it's a really good conference. Yeah. Really excellent.
Thank you. Well, our motto, as you know, is learn, connect, get inspired, and
right.
Learning, providing all these courses, all the tools, tips and tricks, connect, just obviously getting all the stakeholders together and connecting students with mentors and getting inspired, bouncing ideas off of each other. What do you think, how do you think AltiumLive contributes for engineers to become better engineers?
Engineers learn most of their circuit design tricks in school. And those that they don't learn in school, they're usually able to pick up from other engineers on the job. Nobody really teaches printed circuit design. And printed circuit design is the real secret to success in a circuit's working. It's fairly easy to create a circuit schematically that will function. As Eric Bogatin said in his keynote the other day, once you have the circuit designed, the rest is noise. And you can control that noise with proper printed circuit design, or you cannot control it with poor printed circuit design. And board design is critical. It's probably the most critical link right now in the whole structure. When I was a young engineer growing up, circuit board design was a connect the dots function. And it was easy and it was straightforward and you could do almost anything. We broke every law of physics and yet they still worked. Today, that's not the case at all. Parts are so fast, systems are so fast. They have blazingly fast rise times, and that means everything on a circuit board is a controlled transmission line and has to be treated as such. And the end result is, if engineers don't design that way, they're going to have serious problems. So that's what I love about this and for example, PCB West. Both of those conferences have a lot of information on how to properly design circuit boards, and that's what engineers need to equip themselves for the future.
So you had a class on EMI at this AltiumLive. Can you talk a little bit about the contents of this full day class?
It was a full day class, right? And we covered everything from circuit behavior. We talked a minute ago about transmission lines. We got into how transmission lines actually work. One of the things a lot of people focus on, engineers especially, are voltage and current. And the bottom line in reality, it isn't about voltage and current, it's about fields. It's all about where the fields are in the circuit board And they don't actually travel in the copper. That's something many engineers don't know. There's no energy in the copper. The energy is in the space between the copper structures. So when you route a trace, referencing a plane, for example, the energy moves through the space between the trace and plane in the form of fields. And it establishes a voltage and current, but the energy is actually not in the copper. And many engineers don't know that. And part of the reason they have problems is because they don't lay out circuit boards with proper references for all the traces they route. And so they end up getting themselves in trouble. Things don't work, they have noise. And this is also what Eric meant the other day in his presentation when he was talking about, the schematic is one thing, the rest is noise. So I talked during that day about some of the basics of energy movement in transmission lines. From there, we got into proper grounding techniques. Where do you place grounds and power planes and things like that to get the best behavior? We went into power distribution, network design, what kind of decoupling you should use, where it should be, how it should be, those sorts of things. And then from there went into a little bit about the I/O structure, how to set up I/O lines to get the best behavior to avoid EMI, and then a few mechanical things at the end. And that was pretty much what the day consisted of.
So what are the key takeaways that your students in this class could take home and apply?
The key takeaway was what I mentioned in the beginning, that the energy doesn't move in the copper, it moves in the space. And so there were like 60-some people in the class, and probably half of them came up to me afterwards and said, I had no idea. I had no idea that was the case, and I've learned a whole new method for design that will obviously help me moving forward. And that was the key takeaway.
And is there an analogy, is there an analogy to kind of make that more visual, understandable?
Yeah, I guess so, actually. When I was an engineer in school, professors and other students talked about the water analogy, that electricity is a bit like water, moving through a water pipe. And as a young engineer, I saw electricity as voltage and current. And I was puzzled how voltage and current could actually be like a water pipe. But electrical energy movement is like a water pipe, because the water moves through the pipe between the outside perimeter of the pipe itself. Energy is the same way. The energy moves through the space between the trace and plane, almost like a water pipe. So it is very much that sort of thing. That is probably an excellent analogy. Now, once I really understood what energy movement was, then I realized, the water analogy is absolutely correct.
You still designed with tape and mylar?
Years ago, yes, I designed with tape and mylar. Carl Schopke, one of the people who's speaking here, had designs outside last night showing them to a lot of the people, and so many of the young engineers had never seen a tape and mylar design, and they were oohed and awed by this. It was pretty amazing to watch. Yeah. Yes, I started that way, using tape and mylar. That's how I got started.
Yeah, can you talk a little bit about how things changed over time? It's obviously transformed.
Oh, it has transformed amazingly.
But is there something that kind of is important for students to understand about that heritage of tape and mylar?
Well, that's a good point. Again, back in the day, because things were so slow, practically every circuit we worked on was a lumped element. And as a result, that's what gave us the ability to lay things out any way we chose. We had 1- and 2-layer circuit boards that would have a wandering ground trace moving around a board, and that was adequate in those days in order to contain energy, because that's all it took with lumped element circuits. Today, things are distributed. Now, we have two things going on today. One, we no longer use tape and mylar. We have the luxury of excellent CAD softwares today. And of course, Altium is one of the better ones, I think, but there are others as well, and there are many good CAD systems out there. And they give engineers the advantage to be able to move things around much more readily than we did in the tape and mylar days. We had to make firm decisions about where things were going to be and then just do it. And today, engineers have that luxury, which is great. It's absolutely phenomenal to have the freedom to okay, I want to do it this way. No, that's not quite what I want. Move it here, move this, move that. And then start routing once you get everything where you want it. But because things are so fast today, CAD tools give us the freedom to do all these things. And then of course there are good simulation tools to go with it. Tools to be able to simulate transmission lines, to simulate power bus behavior, and all of the things that really are critical to make designs work. So it's really nice to have that today.
What do you think a student can take away? Would it still be useful for a student to know about tape and mylar nowadays in order to make?
I don't know that there's any benefit for students today to know about tape and mylar. I mean, it was cute, you know, it really was. I have a taped artwork on my wall of my office at home. I taped it was the last taped circuit board I ever did. It was 1984. Shortly after that, I went directly to CAD. And this was a 2-layer circuit board with 200 ICs on it. So it was a big circuit board. It was a VME bus design that had 250 I/O pins that went to a backplane and other VME boards plugged into the backplane. And it was like a 14 by 16 board, and it was a processor board that today would be on a 2 by 2 inch board, because ICs are so much smaller and so much faster today. That same board today would be probably 2 or 3 inches square, not 14 by 16. But it's a fascinating thing to see, and it's enjoyable to look at, and that's why these young guys last night were so taken by Carl's taped artwork. But I don't know that there's any real advantage to them other than just to know the history. You know, the history is really fun, but beyond that, there's no technical advantage to knowing it. We are lucky today to have such great CAD tools. And I think Altium 20, just watching the demonstration they gave today, it looks like it's going to be a marvelous tool for the future. They've added some really nice features that will help routing and all the other things they're doing, and collaboration, to be able to, engineers to collaborate from different offices or different parts of the world. Just the things they're doing now are marvelous.
Yeah. So obviously we got a glimpse of the future, of how PCB design will be like.
And future designers are going to be double E's. I mean, when I was growing up, I happened to be a double E who became a board designer because that was my passion. Most of the designers of my era were technicians who were good at reading a schematic and figuring out how to tape a board, or they were artists. Susie Webb, a good friend of mine, was an artist. She grew up as an artist, and that's what she did. And taped artwork did require an artistic touch to do it properly. And so one company hired her simply because she was an artist, figured they could teach her the technical side of it, and they have. I don't know that that's the future of design. I think the future of design are double E's who either have to do their own board layout or who decide, like I did, that's what I want my future to be, you know?
Do you think there is still artistry in today's PCB designs?
Of course there's artistry. One of the things I learned early in my career, something doesn't look right, people don't like it. I think circuit boards have to have a balanced, crafted, artistic look to them, or people will look at them like, what is this thing? And they won't be attracted to them. Products that have the right look attract people. And so even the circuit boards in the packages need to have at least a balanced, artistic, sometimes almost futuristic look, because that attracts people to them. And all companies want to attract people to their products. So yeah, I think there will always be a need for some amount of art. It'll always be some art and some science, probably, always.
So what do you like to do when you don't design, or you're not?
What do I like to do when I don't design? Well, as I mentioned to you at the onset, I mentor high school and middle school students in Science Olympiad, which is really a lot of fun, teaching young people about science and how to apply the science they've learned in school to projects. You know, how to make something work based on the science they've learned. That's a great deal of fun. I enjoy that. My wife and I travel a bit. We just got back from a 12-day cruise through Europe, which was fun, from Amsterdam to Switzerland. We went through Germany and France. It was just great fun. I like to play games like chess. I've always been a fan of chess. So just, you know, casual time doing stuff like that. That's pretty much how I spend my time. I work so many hours. I retired 5 years ago from full-time work in industry, and I was going to just sit back and take it easy. I thought, well, I'll consult a little. And I've been literally busy full time for the last 5 years. So it's worked out far better than I ever expected it would.
Well, I'm happy for you that it worked like that. Yeah.
Yeah, it's working well.
Fantastic. When you work with students, what are some of the most common questions or most interesting questions that come across?
They like to know things like, what was it like when you were young, studying science and so on. In fact, one example was some of the students in our Science Olympiad group asked about, they said, we have calculators and things today, even on our cell phones, to do very quick calculations. How did you guys calculate stuff when you were young? And the answer was, we used slide rules. One of them said, slide rule, what's a slide rule? And I said, it's two sticks that move, and they literally allow you to multiply and divide or take squares and square roots and cube roots of numbers. And they said, how's that work? So I have two slide rules. I took one of them to Science Olympiad one day, and I explained to them how they work, and they were just fascinated by this. One of them looked at it and said, how can you move a stick and multiply numbers? And I said, it uses logarithms. They said, what are logarithms? And I explained a logarithm is an exponent. And that's how a slide rule works. It uses exponents, it adds the exponents, and then takes the antilog of the exponents to get the answer. So it multiplies by adding exponents. When I explained it to these kids, they were just blown away. And the best part of all, they understood. They're geeky enough, just like me, that they understood exactly what it meant. But those are the kind of questions they ask, and they ask about how were things when we were growing up. Constantly curious about what was life like when you were young, that sort of thing. Science questions, they pretty much already know most of that. So they're more interested in our personal lives than in our science.
Yeah, what is different from the kids nowadays with all this information available to them compared to when it was back in the time?
Kids today are so much better informed. I mean, they have access. They're constantly bombarded, actually, by information. And they have access to so much information that we didn't have. I mean, I was probably 20 years old before I understood half the things that 12 and 14-year-olds today understand. They have so much available to them, ways to learn and ways to pick up information. Not just the internet, but there's so many social media concepts that kids can use to talk to each other and learn from each other in different countries and in different states around it's amazing. Kids today are so much more advanced than they were when I was a kid, and they're mature. I noticed that with the Science Olympiad kids that I work with. They're cute and they're fun and they play. Some of these are 12, 14-year-old kids, and they play like 12 and 14-year-old kids. They jump around and they goof off. But they're also very serious. They have serious moments, more so, I think, than I did when I was young. They have a really serious side. So I think that's a couple of the big things today.
What would you tell a parent? How can you inspire your grown-up kid to keep that curiosity about the world?
Oh, that's a good question. My kids have been grown up for years, and we just encouraged, my wife and I encouraged our kids to constantly look at everything around them. Just open your eyes and your mind to everything around you. And I think I would tell parents that same thing today. My kids were constantly curious because we encouraged them to do that. And I think that's what I would encourage any parent to do. Just keep your kids' minds open and encourage them to learn from every avenue they can. The more you learn, the more you'll have a handle on how to treat life as you move forward.
An aspiring engineer, what would you tell them to keep doing in order to become the best engineer they can possibly be?
Read well beyond what you learn in college. When I graduated from college, and many people have heard this story for themselves, because this is a common theme with the speeches that are given at graduation for college students. The guy who did our commencement ceremony said to all of us, he looked at us and he said, now the learning begins. And I thought, what? Wait a minute, what have I been doing for the last 15 years? What do you mean now the learning begins? Are you serious? And he was right. The first 2-3 years I was out of college, I was able to muddle by on what I'd learned in college. But beyond that, it's There's so much more to do. I own over 120 technical books, and I've purchased most of them since the early 80s. I've learned so much from them. I owe much of what I am today to the knowledge I've picked up from others by buying their books and understanding what I could acquire from that. So I would encourage all college students to constantly learn. Those engineers who get into a job in management says, I want you to do circuit boards as well. Don't just do circuit boards. Talk to the manufacturers of the boards. Talk to the fabricators, the assemblers. Learn what will make their job better and easier, because that'll reduce the cost of your product. Learn about transmission lines. Learn about energy movement. Learn about all of the things that the circuit board does, because it isn't just copper and fiberglass. It is a functioning, working element. And if you don't understand how it functions, you're lost.
So are there any books in specific that you could recommend?
In this EMI class I did the other day, I recommended 6 books. And one of them is a book that is about a little over a year old, year and a half maybe, by Ralph Morrison. It's called Energy Movement, oh darn, I've forgotten the exact title. Energy Movement, Fast Circuits, or something to that effect, but Ralph Morrison was the author. Ralph sadly passed away about a month and a half ago, but he was in his 90s. One of the smartest people I ever met in my life. He's the one who opened my eyes to where energy actually moves in circuit boards, because I used to chase the voltage and current like everybody else, and we would have noise problems or EMI problems, and we didn't fully understand them because we didn't understand where the energy was in the circuit board. Ralph, through his teachings in his books, taught me what's really going on in the circuit board, and once I understood it, all the problems I'd ever had suddenly evaporated. I instantly, literally, after I read the first book of Ralph's that I read, I instantly understood why every problem I'd ever seen occurred, and I instantly knew what I should have done to solve it. So I would encourage young engineers to get that book. Another one is Real World EMI Control by Dr. Bruce Archambault. Henry Ott's book on EMI control is always a good choice. There are a number of good books. Those are 3 that any engineer could start with, and just Lee Ritchie's books on high-speed design would be excellent choices. So there's a number of great books out there, and those would be 3 or 4 to start with.
How did you get into engineering in the first place? Do you have like a story, or do you remember?
Oh yeah, of course I remember. I was talking with Judy Warner one day, and she asked me, she said, when did you know you were going to be an engineer? And I said, well, it started when I was 5. We were trash picking, of course, what do 5-year-olds do, right? And I found an old clock, and it wouldn't run, and I took it home, and I took it apart and played with it for 2 weeks. I was 5 years old. I had my mind made up, this clock is going to run. Well, I never got it to run. It had a broken mainspring. It was never going to run again. But I learned a lot about it in the process. I learned a lot about the mechanics of gear movement and that sort of thing. And it just kind of escalated from there. I was always, fortunately, very good at math. Math comes to me so naturally, it's ridiculous. Whenever I was tested in school, I was always in the 99.5 percentile, in math and science, because those were just so natural to me. And I just knew growing up that my passion was science. And in high school, I decided this is it. I'm definitely going to be an engineer. I headed to engineering school, and the rest was history.
That's a wonderful story, yeah.
And there are a lot of young people today who have that same passion, And I think, the real key in life, my guidance counselor in high school said to me one time, what do you want to be when you grow up? I was, I think, in the 10th grade at the time. And I hadn't thought about engineering to that point. And I said, I don't know. I said, what would your advice be? And he said, pick out something you love and find a way to make it your occupation. If it's art, be an artist. If it's language, be a teacher or be a linguist. If it's history, get involved some way in defining history or teaching history. If it's science, be an engineer, a scientist, a chemist, whatever. And I realized when I was talking to him, I love math and science. And the interesting thing is I've never had to look for a job in my entire career. Jobs have just fallen in my lap. It's unbelievable. It's unbelievable. Because I love it and I've become good at it. And when that happens, people seek you out instead of the other way around. It's great.
Engineers in the workforce out there, you know, in a career, building a career. Is there some wisdom that you can give to them of how, I don't want to say how to behave in the work, but how to be wise about their career choices or their everyday work?
Engineers tend to be shy. You really have to overcome that. Everything in life is a sales job. Even though I'm an engineer, I've had to learn to become a salesman because you have to learn to sell yourself. If you can't sell yourself, nobody's going to be buying. And that's really the bottom line. And engineers need to pick up the traits of the people who are in the sales force. They really need to learn a lot of those traits. Now, they don't need to be as outward and as forward as salespeople typically are, but that they still need to know how to promote themselves and how to sell themselves. The science part to an engineer will come naturally because engineers are just naturally science people. The rest of it doesn't come easy. So many engineers I've known are timid and shy and don't want to step out into the limelight. You must step out into the limelight.
I can imagine that it's hard for somebody who is shy to find a way of where do I start to learn to sell myself? Where would you send them now to get started in?
You know, that's a good question, and I don't honestly know because as a young engineer, I was painfully shy, and I had a really hard time breaking out of that mold. But I realized if I was going to get anywhere in life, that I better be able to promote myself. And not just getting jobs, but getting advancements within jobs, being able to get a raise, any of those sorts of things. But the last full-time job I had was at L3 Communications, a division of L3 Avionics. And shortly after taking the job, myself and another board designer were given the opportunity to solve a fairly major problem in a system that was failing. And we were able to solve it where none of the other engineers on the staff were able to do that. Management sort of noticed, but not really. But I made sure come raise time that they were aware of it. And we both got giant raises that year. So it's hard to do, and I don't know how to tell somebody to you know where to go. You just have to learn not to be shy and to step up, put your best foot forward, put a smile on your face, and make it happen. You sell yourself. It's about selling yourself. You know exactly what I'm talking about. I don't care whether you're an engineer or what you do. You have to sell yourself.
Let's talk about engineering in general. What excites you about engineering?
There's not much about engineering that doesn't excite me. Obviously, most of all electronics, and in particular printed circuit board design. I've really, over the last 30 to 40 years of my career, made that my solid passion is circuit board design. I try to learn everything I can about it. The electronics part of it is fairly straightforward, and I understand that. That's actually not that hard to understand. So I focus on things like design for manufacturability, design for test, design for cost, design for ease of everything. You know, you have to learn about every little aspect because it really does all come down to money. And when you design circuit boards correctly, they will work. The company won't have problems. They won't be chasing their tail trying to run down a problem. They will be less expensive because they will be lower layer count. They'll be designed properly. They'll be easier to fab, easier to assemble, and everything will just work. So my passion really in engineering has been about circuit board design. And I would encourage any double E to make that at least part of their passion as well.
What drew you towards printed circuit boards? I mean, the first thing was the clock, right? It was mechanical.
Oh, sure, yeah. I mean, it was the electromechanical side of life, and I think that's what it was. I mean, I was satisfied as a young engineer. I actually started as a technician with a 2-year degree. I worked for Xerox for a while, And I left there not because I didn't like Xerox, it was a great company, but they wanted me to wear one hat at a time for 6 months in a row. And I was young and eager and wanted to wear 25 hats a day, and that wasn't going to happen there. So I went to a small company where I could wear 25 hats a day. And as I got involved with testing and building and troubleshooting problems, I ended up getting in field service. I just kept getting drawn more and more toward the circuit board side of things because everything about it made me curious. How does it work? Why does it work? You know, that sort of thing. And I was just drawn into it. I was sucked into it, and I've been there ever since. But I like the challenge, especially back in the taped artwork days. I like the challenge of looking at a schematic and imagining in my mind, how am I going to lay that out on a circuit board to make it function? And I love that challenge of the puzzle. It's about the puzzle of getting from point A to point B. I love puzzles, and I still to this day work every morning when I get up. Because I'm semi-retired, I usually take about an hour to eat breakfast, and I almost always work either a Sudoku or a Ken puzzle while I'm having breakfast, just because I love puzzles. So anything that has to do with puzzles has always appealed to me, and circuit boards are a puzzle. They really are.
How do you think Altium as a company, or companies like Altium, could help engineers become the best engineer they can possibly be?
Well, Altium is already doing that, and actually so are several other CAD companies, by providing software that is fully functional, that allows the engineer to go from idea to schematic, to evaluate the schematic realistically, to from the schematic come up with a net list that can be turned into a circuit board, to have tools that allow them to analyze the circuit board while they're placing components, thinking about, okay, how am I going to route this, maybe simulate this or that. Those are all things that CAD companies in general, Altium included, are doing a great job with these days. And Altium has actually probably advanced over the last 5 years more than any other CAD company. I mean, Altium's always been a good tool. Prior to Altium, I used a PCAD 2001, 2, and 3 back, which was the predecessor to Altium Designer. And that was probably my favorite tool I ever used. And Altium is an equally good tool, with just, it has more good features today than PCAD had back in the day. But Altium's really advanced tremendously in the last 5 years, and they're doing a wonderful job helping engineers solve that puzzle. And that's what it comes down to, solving the puzzle.
Our developers will be happy to hear that.
Well, good, good. And they deserve the credit, because they have done a wonderful job. You know, the demonstration that was given this morning by Ben and Chris, that was really a neat demonstration. And I know both of those guys are hard workers, and they've done an excellent job on the development of the tool. I've known Ben for many years. He's a great guy. Great guy.
So just to close, I want to close with the question of, how do you see electronics in the future?
It's going to keep getting faster. I see companies keep shrinking die, and they shrink die so they can get more transistors in a given space. But when they do, the IC gets faster and faster. So even when clock rates aren't high, IC speeds are still high. And the end result is that everything that goes on a circuit board in the future is going to be fast. And so every engineer will have to understand high-speed design, they'll have to understand noise control, they'll have to understand EMI control, and that's also part of what Eric meant the other day, is it's beyond the schematic, it's about the noise. And every engineer is going to have that takeaway in their life. Any engineer who's doing electronic design, their future is high speed. It's that simple.
Looking at society and how electronics and the internet and many other factors change society, do you have some comments on that?
I did a study recently of the Internet of Things, IoT. I was shocked to find there are over 20 billion devices, IoT devices, on the internet today. And by the end of next year, 2020, it's expected to be 25 billion. And by the end of 2030, it's expected to be 500 billion devices connected to the internet with a cost, a value of, I forget the number, I think it was $100 trillion. I don't know if you've ever thought about $1 trillion. If I said I'm going to give you $1 trillion, but to keep it, you have to spend $1 million a day, 1 million a day. After a while, that would become challenging to do because there's only so much stuff you can buy, right? At $1 million a day, how long do you think it would take you to spend $1 trillion? 2,700 years. That's how much $1 trillion is. And the Internet of Things by 2030 are going to be worth hundreds of trillions of dollars.
So how is it going to work out? Are we going to eat the Earth crust in order to turn them into devices? Or?
I don't really know. And the future is going to be rocked by artificial intelligence as well. A lot of people think that artificial intelligence means reasoning. It doesn't necessarily, it just means thinking. Reasoning is the ability to look at one thing and then another and put the two together and come to a third conclusion. That's reasoning. Thinking is being able to go deep into thought and decide, oh, this is better than that or that. And that's what computers already do well, and they're going to do extremely well in the future because they're doing what's called deep learning. The world, China, the US in particular, have collected so much data over the last 20, 30 years, and they're feeding it to these computers that are designed that have terabytes of memory and operate at ridiculously high speeds that have been designed for artificial intelligence. They're neural networks, and they're feeding them so much data, these computers are going to be capable of actually looking at things and figuring out solutions, not just doing what they're told. So all of these things combined are going to make up the future, and boy, technology is advancing at a scary pace. It's just amazing.
What's your personal philosophy how to navigate through that new technology?
I mean, if you look at where we're headed with artificial intelligence, with quantum computing, with all of these things, and just the sheer volume of stuff that's going to be on the internet, you know, people will have access to so much information, so much data, and computers that operate at speeds we've never conceived. I mean, the future is wide open. I haven't really thought much about that until you asked that question just now, but it almost gives me pause thinking, my gosh, what is the future going to hold? I think young people coming up today are going to have really the world at their fingertips. They're going to have everything they need. I just hope they learn how to use it wisely. You know where I'm going with that. But yeah, computing is getting amazingly fast and unbelievably powerful.
Well, thank you so much for your time, and
thanks
for your presentations and being part of the.
I enjoyed the presentation on Wednesday very much, and I think the group that was there enjoyed it as well.
Fantastic. Thank you, Rick.
Thank you. My pleasure.